Okay, welcome to the post-launch session, and in this session we have the talk by Michelle. She is going to tell us about neutrinoless double beta decay and neutrino mass measurements.
Great, thank you so much. So today we're going to switch topics. We are still talking about nuclear physics, but we're going to be talking about neutrinoless double beta decay, and this is the area that I've been working in for the last 20 years. I've worked on the Cortino and Corey experiments, the EXO 200 experiment, and the NEXO experiment. So you may hear some of my biases creep in. So we'll just start off again the same way that we started off yesterday. How do we understand neutrino mass? And we've already heard about cosmology, time of flight, tritium endpoint measurements. And now we're finally on this last limit on the neutrino mass. And again, this is a different parameter than any of these other parameters. And it's also, of course, different than any of the individual mass states, but that's okay. This is just a cartoon. And so we have this limit of 100 millielectron volts on the neutrino mass that comes from neutrinoless double beta decay limits. And it's a dashed line here because there's a big assumption that's baked into even drawing this as a neutrino mass limit, which is that in order for neutrinoless double beta decay experiments to set a limit on the neutrino mass, the neutrino has to have a Majorana mass. Right, so we're only limiting an effective Majorana mass for the neutrino. You guys have already heard a lot about this. So this is the main goal of a neutrinoless double beta decay experiment, to understand the origin of neutrino mass and to understand whether neutrinos have a Majorana mass, and therefore we throw away the concept of lepton number conservation. We've seen that, Dirac neutrinos are described by this four-component object. There are some problems with including Dirac masses in the standard model because of the way that neutrinos interact. We also have the possibility, because of the neutral nature of the neutrino, that the neutrino is this Majorana particle or its own antiparticle. And of course, these two descriptions are distinct and distinguishable only when we know that neutrinos have mass. We do know that neutrinos have mass thanks to neutrino oscillations. And so following the discovery of neutrino oscillations, interest in looking for neutrinoless double beta decay really exploded. So of course, I'm going to talk a lot about neutrinoless double beta decay. We have seen some other consequences, though, of Majorana masses. So other experimental signatures that we remember from this week for Majorana versus Dirac, potentially. Heard about one just yesterday. Dipole moments, right? But the limits on dipole moments, neutrino dipole moments, are far away from being able to tell us the difference, tell us whether neutrinos are Dirac, for example. So right now, double beta decay is our best bet for understanding whether neutrinos have a Majorana mass. So when I say double beta decay, doesn't always mean I'm talking about neutrino mass. There's also what we might call vanilla double beta decay, or double beta decay with the emission of two neutrinos. So this is a standard but very, very rare nuclear physics process. It's completely allowed in the standard model. And so yesterday we talked a lot about beta decay. Double beta decay is just literally that twice, but at exactly the same time. I know you already had one lecture on neutrinoless double beta decay searches, so I'll review a little bit of what you've already heard, including that the reason that this happens, becomes the dominant decay mode for some even nuclei for which the single beta decay is forbidden. It might be forbidden energetically. So in the case of xenon-136, xenon-136 would normally beta decay to cesium-136, but cesium-136 is too heavy. We see these two curves that happen all over for even A isotopes because of this parabola, mass parabola splitting in the semi-empirical mass formula. And so there's lots and lots of nuclei that will have their primary decay mode as double beta decay. And you'll notice there's also things that look very similar on the other side, right? So this is where things are beta decaying. Over here, things are beta plus decaying. So normally you'll hear people talk about double beta decay, we mean 2 beta minus decays. It's also possible that you would have 2 beta plus decays, or the problem over here, beta plus decays, there's a lot less phase space because you have to create those positrons. So these typically have a lower Q value, a lower phase space, because you pay the penalty of creating that positron. And so it's less favorable to look for these decays on this side. If there's not enough energy to produce the 2 positrons, then these can proceed by beta plus electron capture or double electron capture. So like I said, these processes are very, very rare. And doesn't mean we haven't seen it. So this is actually the first direct evidence for 2 neutrino double beta decay. It was seen in selenium-82, 1987, Elliott, Hahn, and Moe. And this is the energy spectrum where they're trying to fit that double beta decay energy spectrum to their observed data. What do you guys think of that fit? But this was evidence for a selenium-82 2 neutrino double beta decay with a half-life of 1.1 times 10 to the 20 years. These are the kinds of half-lives we're talking about. Right, so this is very, very rare, orders of magnitude longer than the lifetime of the universe. And so looking for this requires a lot of isotope, low backgrounds, and a sensitive detector with good efficiency. If this happens, you don't want to miss it in your detector. So they just got a handful of events in order to make this first observation. There had, of course, been earlier measurements that you heard about last week from geochemical measurements where they could see evidence of the daughter nuclei, but this is the first direct observation. And at the time, it was the rarest natural decay process ever observed directly in the laboratory. So this was done with selenium foils embedded in a gas detector. So we can see since then, we've measured the 2 neutrino double beta decay half-lives of many of these isotopes. I'm sorry this is so small. And you can see 10 to the 19 years, 10 to the 21, 10 to the 20, right? They're very long. Another 10 to the 21 down here. So it gives you an idea. That's the process that we're competing with, very rare. And you'll also notice that these have been measured by a large number of different kinds of experiments, right? So it's a large number of isotopes. Many of them have been measured by NAMO3. I'll talk a little bit about NAMO in just a few minutes. But then we see a lot of other experiments. You'll see many of these again. Some of them are relatively small, specific experiments to look just for the 2 neutrino double beta decay. But a lot of these are actually demonstrators on the way to larger scale 0 neutrino double beta decay experiments. This is actually data from NAMO, and one of the things that we will always do is, again, construct that beta decay spectrum. So here's where we're summing up the energy of the 2 betas that are being emitted at the same time. That's our energy signature, and so there's a fit to that 2 electron or 2 beta energy spectrum, and you can see the statistics have gotten a lot better. Right? These measurements are now very precise. You look at the error bars on those. Something that NAMO can also do is not just look at the total energy, but it can also look at the energies and directions of the 2 electrons individually. So what we see here is a plot of the events versus the cosine of the opening angle between the 2 electrons. And so this also agrees very well with the prediction from nuclear theory of what opening angle we should see between those 2 electrons. Most double beta decay experiments can't do this. So this is a very special aspect of a NAMO that we'll come back to. So the way that NEMO works, this is the upgraded version of that early experiment where we've got foils. So there's a set of foils here. So thin foils of our isotope of interest, our double beta decay isotope, inside a tracking detector. And so you get these lovely tracks. Inside a magnetic field, so we get the curvature of our charged particles being emitted. And this gives us a very nice signature that we're actually seeing two particles being emitted at the same time from the same location, right? This helps us get rid of background, which is a really important thing to do when you're looking for a decay that's this rare. And then finally, a calorimeter here to measure the energy. So the tracking is to be able to measure that opening angle, which would be the angle here, and the calorimeter to make the energy measurement. Okay, so now we're moving on to the decay that actually tells us something about neutrinos. Two neutrino double beta decay, really interesting nuclear physics, not telling us anything about neutrinos. But since we have this already, we have these two electron antineutrinos being emitted at exactly the same time, we can also have this competing diagram. So here's our neutrinoless double beta decay diagram, and we see that exchange of a light Majorana neutrino. So here we see the emitted electron antineutrino flip its helicity and be absorbed over here as an electron neutrino. So in order for this to happen, this is a lepton number violating process, and it can only occur for a Majorana neutrino, and it can only occur for a massive Majorana neutrino. That should be obvious. So we need that helicity flip there, that the mass of the neutrino is going to come into the rate of this decay because we need to be able to flip the helicity when we do that. So this ends up being the most sensitive probe of the Majorana nature of the neutrino because we basically take advantage of this physics on a nucleus where we can scale up now with the number of nuclei. We get a very intense source. And we can also control the backgrounds very well. And so we have the same candidate nuclei down here. It's exactly the same thing. These two processes are going to compete with each other, and this one's always going to win in the same nuclei. Okay, so the double beta decay spectrum, the two neutrino spectrum, we see that broad spectrum continuum. It's got a different shape than the beta decay spectrum, but has the same, we got the same idea, right? We've still got neutrinos carrying energy away, our detectors aren't seeing them. So we see this broad energy spectrum of the sum of the beta particle kinetic energies. That's what this is representing. So just like in beta decay, there's just two of them now. And what neutrinoless double beta decay would do, this goes back to being a sharp peak in our spectrum. Now we've got no neutrinos. So there is our neutrinoless double beta decay peak. Our betas have all of the kinetic energy available in the reaction, so that peak sits right at the Q value. The Q value for these reactions is actually really easy to measure because the Q value for beta decay or double beta decay is just given by the difference in the atomic masses between the parent and the daughter. So we know exactly where to look for this peak in the spectrum. Right? We don't have to worry about that fuzzy little low intensity region at the end of our two neutrino double beta decay spectrum. So this cartoon here makes this look really easy to look for, right? We just go, we know where to look for a peak in our spectrum, it tops out really nicely, no big deal. The problem is we haven't actually seen this, so I'm just making up some normalization here. And the normalization here is one of these for every 100 of those. And we have blown past that a long time ago. So this is not a realistic cartoon of what we're looking for in the current and next generation of double beta decay experiments. So this would be 100 times more rare than this. The region that we are pushing toward now, that we're in right now, looks a lot more like this. So now it's looking a little bit harder, right? So I think last week someone asked the question about worrying about this two neutrino tail. That two neutrino double beta decay spectrum tail does go all the way up to the Q value. If you're a detector, you have finite detector energy resolution, so it can start to overlap your peak. This is what happens when we normalize to something like one of these for every million of these. And that's really where we live right now. So here we have a finite detector resolution of about 5%. And we can already see that while these aren't completely overlapping, like we don't love this, right? This isn't great. So this starts to motivate why, as we push to longer and longer half-lives, we need to really worry about our detector energy resolution. We want that to be as narrow as possible. So that tail is always going to be there. It's not always going to overlap with our peak. How much it overlaps with our peak really depends on the ratio of these two, right? For a given energy resolution. So let's just see what NAMO3 saw when it looked for Neutrinoless double beta decay in molybdenum 100. And this is a sum energy spectrum. So this is, again, the total sum spectrum. So it's adding together the energy of the two electrons that are emitted. It can also look at those independently, but it's adding them together to give us our normal Neutrinoless double beta decay, or double beta decay spectrum. And you can see the biggest thing in their spectrum is, in fact, that 2 neutrino double beta decay signal. And if we zoom in on the Q value here, that endpoint, that's at about 3 MeV in molybdenum 100. Their signal would look like this dashed line. And the data is not consistent with the signal there. Right? It's completely consistent with their background. But we can also see that because their energy resolution in their individual detectors vary from about 6 to 8%, this is quite a broad spectrum, and we do have 2 neutrino double beta decay events that bleed into our signal region, right? So that's kind of the downside of having a detector with poor energy resolution. Even though NAMO3 can do many other beautiful things, it's not so good at energy resolution, right? Based on this, and based on about 35 kilogram years of exposure, they're able to set a half-life limit of 1.1 times 10 to the 24 years at 90% confidence level. Because they have access to those 2 electrons and their opening angle, they can actually test whether this is consistent with the light-Majorana neutrino exchange mechanism, which is this diagram, essentially. Not everyone can do that. So here's what we mean by the light-Majorana neutrino exchange mechanism. I don't know why I backed up for that. So here again, we just see the 2 W's, the betas being emitted, and the exchange of the light-Majorana neutrino. So that's what we talked about before. We often talk about this as the mechanism because it makes sense, right? It directly ties the double beta decay, neutrinoless double beta decay phenomenon to the existence of light-Majorana neutrinos, right? We can see it right there. But this is really an assumption. If we do see neutrinoless double beta decay, we won't know that this is the diagram that's responsible. So we're assuming that this is in order to go further. What our experiment will actually measure will be a half-life or a rate, right? So 1 over the half-life gives us something like a rate of neutrinoless double beta decay. If we want to turn that into the underlying physics, if we want to relate it to neutrino mass, we first assume the mechanism, and then we can calculate. So in this case, if I assume this mechanism, I can write that my rate is equal to a phase space factor proportional to the Q value to the 5th power. So having big phase space is favorable. We'll have a higher rate, which is good. That makes it easier to detect. A nuclear matrix element. So we need to know something about the nuclear physics. This actually turns out to be a hard theory problem. So I'll show you where we're at with that. And then finally, the effective Majorana mass, the physics, the underlying physics that we would want to get at. Right? This is what lets us extract those limits on the neutrino mass. So phase space, you've seen this plot before. And what we're looking at here is the range of Q values for many of the commonly studied isotopes. And as was pointed out last week, calcium-48 kind of pops out there, right? That looks like a great one to study. We've got lots of phase space. It's going to have predicted a relatively high rate. It's a good thing to look for. And so for a given mass. And certainly there are people who are looking for neutrinoless double beta decay of calcium-48, but there's not very much of it. So it's actually really hard to enrich. So we kind of put that one aside, just practically. That would be a difficult experiment to do. The other one that pops out is tellurium-130. There's a lot of tellurium-130. It's 30-some% of the naturally occurring tellurium. So maybe you don't even have to enrich your source to do this experiment. And in fact, that's what the Quarry experiment and the Snow Plus experiment are doing. But then in here, there's this like pack, where all of these are kind of, there's a decent amount of them, 10% natural abundance, and the Q values are all in a pretty favorable range from 2 to 3.5 MeV. And so we also have people tackling these, in particular germanium-76 and xenon-136. We already heard about the tin-124 experiment last week. Now we move on to these nuclear matrix elements. So I said this has to come from nuclear theory. And this has been a big effort for many years. In fact, there's been a big investment in the nuclear theory community to try to reduce the spread on these. And part of what's going on is there's just a lot of different ways to tackle these. These are big nuclei. And big nuclei are hard to model and to understand. So we do have nuclear shell model calculations, but it is really hard to do ab initio calculations for large nuclei. So we also see things like quasi-random phase approximation and various enhancements to the nuclear shell model. And so overall, based on each of these techniques, we may still see a big spread in what the possible nuclear matrix elements are. And there is an effort to reduce the uncertainties on those. Calcium, again, looking really good, right? The spread in the uncertainties is nice and small. So it would also be relatively easy to interpret a result in calcium, but alas, not so practical. But that can actually be a driver for selecting these. An experiment that's easier to interpret would be better. So if they were very narrow, that would be a way of picking, like what would be a preferred one to look for. So basically, theory will keep pushing on these, and they're doing lots of techniques. In fact, the propagator is totally different for this decay than for true neutrino double beta decay, where we don't have this virtual particle exchange. So this actually probes much higher energies. Right? So true neutrino double beta decay does not give us a handle on those neutrinos double beta decay matrix elements. They're not the same at all. In fact, we want higher momentum transfer processes. So some of the inputs that people give for neutrinoless double beta decay nuclear matrix element calculations are things like muon capture at high momentum transfer. So there are certain experimental results that are used as inputs by the theory community to test their models. But this is a very active area of research, and this conference has been going on for a few years now that's completely focused on matrix elements for double beta decay experiments. Finally, we get to the neutrino physics part. So there's our m beta beta. This is another effective mass parameter. And in this case, this is a coherent sum over the mass states with their mixing. So this is a particular parameterization of the PM&S matrix. And we've just written out what m beta beta is. And we've got 3 CP phases. So let's take a look at the PM&S matrix that we're talking about. So we're, of course, measuring our mixing angles from neutrino oscillations. We're measuring our mass splittings from neutrino oscillations. We're inputting all of that into our calculation. But there's something extra in the PM&S matrix here. Something look funny? 2 extra phases. So these are called the Majorana phases. As I know you've already been, you can tell by looking at the matrix, and you've also been told several times, these have nothing to do with neutrino oscillations at all. Neutrino oscillations are completely insensitive to these because they're on the diagonal. But they only come in when we have Majorana neutrinos, and they affect neutrinoless double beta decay. So there are 3 CP violating phases. We just threw delta in with the other CP violating phases. 3 CP violating phases now, which we have to treat as unknowns. And so we just allow them to vary. So we end up with this expression here, where if we let these vary maximally, we could basically get terms that are, plus or minus here and here. That gives us the spread. It could be anywhere in between those two. So what we want to do now is draw this phase space as a function of the lightest neutrino mass. So first we'll assume the inverted ordering or inverted hierarchy, which, maybe is a little disfavored these days, but we still have to take a look at it. And when we do that and we let those CP vases vary maximally, we end up drawing out these 4 curves. And they have a lot of overlap, right? So but there's actually 4 lines here. And what we see is that as we go down in our lightest neutrino mass, this comes down and then plateaus. That's the beauty of the inverted hierarchy. We end up with this minimum that's at about 10 millielectron volts. So if you can just probe down to 10 millielectron volts in M beta beta, then we could completely cover the inverted hierarchy. That would be nice. If we knew we lived in the inverted hierarchy, this would be a great target. Let's see what happens when we do the normal ordering. It goes all the way down. There's cancellations here. So in this case, we draw again the 4 lines, and we see that for some combinations, there are cancellations here. And so that means that there's no natural end to where we stop looking for neutrinoless double beta decay in the normal hierarchy. It doesn't mean that if we're in the normal hierarchy, it's not worth looking for double beta decay, because there's still a ton of phase space at higher masses. In fact, if we plot them together, and we also include, okay, this is sort of an old fit, but things have tightened up a little bit. But with errors included, this is sort of the total phase space that we have available to us. And remember, we only draw the horizontal lines on this when we do neutrinoless double beta decay experiments. So everywhere that there's inverse hierarchy phase space, there's also normal hierarchy phase space. So we don't determine the hierarchy from a neutrinoless double beta decay experiment, right? These phase spaces overlap. It's still interesting if we get here. When we don't know the hierarchy, once we know that we're in the normal hierarchy for sure, this target will become less interesting. But this is still sort of a natural target to want to get to. We could also plot this versus the sum of the neutrino masses, and then we could push in from this direction using cosmology measurements. So that's another way that we can have complementarity between these different ways of different kinds of neutrino mass measurements and neutrino property measurements. Okay, so when we're looking for double beta decay, we have this conversation all the time about the inverter hierarchy and the normal hierarchy, and people just want to know, what's the chance that we're going to find neutrinoless double beta decay in the next generation of ton-scale experiments? So I'm kind of jumping ahead a little bit. And these 2 papers doing Bayesian analysis of discovery potential of neutrinoless double beta decay experiments came out one day apart in 2017. So 2 people just happened to have the same idea at the same time, 2 groups. And here's basically what one of them did. So we're taking a marginalized posterior distribution for M beta beta and M latest for both the normal and inverted hierarchies. And basically just populating parameter space. And what you see here is, we're taking into account existing limits, which are up here. So we know it's not going to be up here. This is already ruled out by existing experiments. But what we also see is that, okay, this is very much because of the prior. What we also see is that, it's disfavored down here at light masses. That's 100% because of the prior. There's just the way it is. But we also see there's not a lot of phase space down here. This kind of makes it clear that this part of the phase space where we have cancellations is very unlikely, unless, of course, there's some physics or some symmetry that's driving us down there. But if we're just assuming that things are randomly distributed, then it's actually really unlikely that we need to go all the way down there. It could be. There's just not a lot of phase space down here. This is a little bit of like a distorted view. So I think that's the main point I wanted to make about this. You can go a little farther with this analysis and look at the discovery potential for these different experiments. So this is given their sensitivity projections at the time in 2017. And you can see the discovery probability for both the inverted and the normal hierarchies for some of the planned ton-scale experiments. And notice that for especially the largest experiments, Legend, Cupid, and Nexo, not only do we have very large discovery probability in the inverted ordering for all of these, right? Almost 1 or 1 in some cases. We also have more than 50% discovery probability in the normal hierarchy. So that's sort of what I'm trying to point out. There's still a lot of phase space for Neutrinoless double beta decay probe, even if we know that neutrinos are normal ordering. So that can be a big misconception that people have about double beta decay. If the inverted ordering gets rolled out, it's not worth doing. Not true. Okay, and now I just want to talk a little bit about how that phase space can get messed up. So, for example, if there's sterile neutrinos get folded in, and the phase space looks totally different. So this is the difference for normal ordering between 3 nu and 3 plus 1. And just a caveat here, this is plotted against the sum instead of the lightest, so that's why the shape is a little bit different. But it changes completely the phase space. And it's not just that sterile neutrinos that could give us a different probability of observing neutrinoless double beta decay or a different rate. We could have another mechanism that's primarily responsible for neutrinoless double beta decay. So here's just a few examples invoking different lepton number violating physics. A lot of these searches will be complementary to searches at the LHC, for example. Basically, neutrinoless double beta decay is complementary to searches for any kind of lepton number violating physics. And so when we eventually observe neutrinoless double beta decay, we won't know what diagram's responsible. So, we can always interpret it in the view of the latest or the light Majorana neutrino exchange mechanism, but we shouldn't limit ourselves to just thinking about that. So in some cases, we can actually determine the mechanism if we're able to measure the opening angle. Maybe not determine, that's probably a bad word. We can rule some mechanisms out if we can measure the opening angle. It will also be useful to measure in multiple isotopes. And it will also be interesting to measure some of those double beta plus or beta plus electron capture, double electron capture for this. But yeah, this is an important thing to keep in mind. So even though we won't know the mechanism, how is it possible that we say that the observation of neutrinoless double beta decay always implies that neutrinos are Majorana particles? Well, we have this black box theorem from this famous paper down here. And so if we now we've turned our diagram on its side. And so here's our diagram for neutrinoless double beta decay. And whatever physics is responsible for the neutrinoless double beta decay goes in the black box. We can take this diagram and we can twist it around. We've still got our same black box physics here, but it lets us turn an electron antineutrino into an electron neutrino. So anything that goes from electron antineutrino to electron neutrino, this is a Majorana mass term. It's not a big Majorana mass term, and the calculation is actually explicitly done in 2011 just for fun. It's tiny, tiny contribution to a neutrino mass, but anytime we see physics that lets us do this, it means we get to do this. It means we have a massive Majorana neutrino. And like I said, it is really complementary to other kinds of searches. So for example, we could draw a totally different phase space based on 10 TeV right-handed neutrinos in the minimal left-right symmetric model. And for example, this is where this came from. And so we get a different phase space there. And in fact, we're testing parameter space this is a model that's not ruled out by the LHC, but that they could look for at the LHC. And if we have this alternate mechanism that has now 10 GeV right-handed neutrinos, suddenly that can dominate over this light Majorana neutrino exchange. So the light Majorana neutrino exchange is always there in gray, but then this other phase space is also there. And once we pop in a 10 GeV right-handed neutrino, again, not ruled out by the LHC, at least not in 2018, this becomes dominant. So we have this phase space up here now. And that is very much in the testable region for neutrinoless double beta decay experiments. So very complementary to other techniques. And so basically, because we have this black box that we can tuck things into that has basically access to high energy, when we are ruling out light Majorana neutrino masses, what we're really doing is we're ruling out heavy physics. We can stick heavy new physics in there. And so we're pushing light Majorana neutrino mass space, but we're also pushing in the energy scale of whatever lepton number violating new physics that you want to stick in there and test. This is all just to say that this is interesting to look for, regardless of what we know about neutrino masses. So it's interesting, it's motivated by the neutrino masses. It's also motivated by looking for a heavy new lepton number violating physics. And here's another example from Michael Ramsey-Mussoff's group, where they're looking at another particular model. And you can directly see the complementarity between the LHC searches, which are here in these red bands that are curved, and the parameter space tested by current and future neutrinoless double beta decay experiments. And we see that they are very much testing the same kind of parameter space. And in fact, the double beta decay is probing it to high energies. So always new physics, regardless of what's responsible for that new physics, regardless of what the mechanism ends up being, even if we never know what the mechanism is, always new physics there. So experimental search. We already saw some of this. We'll just review quickly. What do we want to do if we want to search for neutrinoless double beta decay? And we remember that we're looking for this tiny peak at the Q value. Well, we want lots and lots of atoms. We want that very intense source. So we want a large exposure. Exposure is just mass times time. So 10 ton years is the goal for the next generation of neutrinoless double beta decay experiments. We want good energy resolution because we don't want that 2 neutrino double beta decay tail interfering with our 0 neutrino double beta decay signal. We want to avoid this. Energy resolution can also help us discriminate between our signal and background, right? The narrower your energy region is here, the less other things are going to deposit exactly that much energy in your detector. So having good energy resolution is good for getting rid of background. Obviously, we want high detection efficiency so that we don't miss any of these very rare decays. And we need a low radioactive background, because what's missing in this picture is actually the wiggly background of whatever else is depositing energy in your detector. And then finally, it'd be nice to have some other event signatures. So for example, in NAMO3, we saw the event signature was the tracks of the 2 electrons being emitted at the same time, right? That's very good for distinguishing neutrinoless double beta decay from any kind of background event, right? So having an event signature that gives you confidence that that was really double beta decay is very nice to have. And we can see there's a lot of very different kinds of detectors that are pursuing this physics. So this is a germanium diode experiment, Gerda, Core, which is tellurium dioxide bolometers cooled down to less than 10 millikelvin and read out as these sensitive photon calorimeters. Again, these are much larger than the ones I was talking about yesterday. And here's Canlan Zen, which I know you already heard about last week, where we have a balloon of liquid scintillator in the very center of the Canlan detector that it has a lot of xenon-136 dissolved in it, hundreds of kilograms of xenon-136 dissolved in it. And then finally, the experiment I worked on, XO200, where this is a low background, single phase liquid xenon time projection chamber. So if you're familiar with xenon-based dark matter detectors, it's a similar approach, but not exactly the same. So we saw already the example of NAMO3, where we had a thin foil embedded in our gas detector. But actually, when we're fighting down backgrounds, one of the best things that we can do is move to this source equals detector configuration, right? Because ultimately, we're fighting against anything that deposits energy in our detector, any kind of radioactive backgrounds. We always need to scale up our source. And if our source, say a foil, is distinct from all of that detector stuff around you, we're going to have a lot of background that's also coming from that detector stuff. In the case of source equals detector, the background is coming from scaling up your source primarily, and so you end up winning in terms of background, and you end up with this figure of merit. This is like the sensitivity, and you can see it goes like the exposure, it goes like the background rate, or inverse of the background rate, the energy resolution. It goes directly with the efficiency. So unfortunately, you only win as the square root of your exposure. So scaling up, you only win by the square root of your exposure. Not so good. And if we remember, when we measure the half-life, that only gives us access to the mass squared. So it was actually fighting square roots all over the place. And then it's also helpful to have a strong mass fraction, which is why most of these experiments are going to have isotopic enrichment of their source. That's what makes them expensive. Because we're fighting backgrounds, we're going to be in an underground lab. And so here's just sort of a survey of the muon flux. This is the vertical intensity of the muons and the total muon flux as a function of our favorite measure of the depth of things, which is in meters water equivalent. So this is just a measure of how deep you are. And if we just look at our total muon flux, which we want to get away from, both for the direct background it can produce in detectors, but also for the activation, cosmogenic activation of our detectors. We see that we have some very shallow sites where we've had past experiments. In fact, XO 200 was all the way here. Not so much overburden, but at that scale it was okay. All the way down to Snow Lab and Jinping Lab. And so this is a very nice place to be, although some of the future experiments will also be cited at, for example, Gran Sasso. We also need low radioactive backgrounds, and that typically means being very careful with our construction materials. So we have sort of heroic efforts to do radioactive background screening of all of the materials that are used to build our detectors. And for example, in XO 200, there were over 300 different measurements that we made just of the materials that we were using to build our detectors. We're also sort of obsessed with cleanliness in ways that aren't always healthy. I don't know if I should show this picture outside of our collaboration, but this is two of my colleagues basically spraying down our cryostat with acid and washing the surface of it. So some of the techniques, these are often like really traditional nuclear physics techniques, neutron activation analysis, low background gamma ray spectroscopy, alpha counting, radon counting, and then also some mass spec techniques. So we basically use every tool that we have in our arsenal, and each one of these is going to be suited for a different sensitivity and a different set of materials. But that's part of what we're doing. So you also heard last week that there had been a claim, I think, of neutrinoless double beta decay observation. And so here's the data. This is a claim for observation of neutrinoless double beta decay in germanium-76. This was done, again, with those germanium diodes. And there it is. Germanium-76 Q value, 2040 keV. There's a nice peak there, 4.2 sigma excess, with an extracted half-life of 2.2 times 10 to the 24 years. What do we think of that? We're done. We found it. I've already got up here. This is a very controversial result, and it actually resulted in the collaboration splitting. Not everyone in the collaboration signed the paper that made this claim, so that's always a good sign. Right? What are some reasons we might not believe this? There's some hints right on the slide. Yeah, there's a linear background model, plus they've modeled all of these nearby gamma rays. We've got these extra peaks. Many of them are from bismuth 214 decay, so well known. Except for this one. Here we have a completely unknown peak. It's not quite as big, but similar significance, very, very close by. And they have no idea where this comes from. So this is part of the danger of these experiments. So when you're probing the sort of longest half-lives ever, you end up finding backgrounds that no one's ever seen before. And in this case, this experiment had no other handles to be able to say, this looks like double beta decay, this looks like a gamma ray. So everything just goes into the same model together. And so, you know, extraordinary claims and extraordinary evidence, this wasn't considered strong enough evidence. They did keep reanalyzing this data. This same subset of people kept reanalyzing this data for a long time. They kept finding bigger and bigger significance. But ultimately, people were very skeptical of this result. And ultimately, the best way to test it is just to do the experiment again and see if it shows up, if it increases with exposure the way that you would want it to, right? If it behaves like a real peak. And then maybe to have a second handle that helps you distinguish between signal and background. So we'll come back to that eventually, but I can just tell you the current leading neutrinoless double beta decay sensitivities include limits on the neutrinos double beta decay half-life of germanium-76 from both the Gerda and the Majorana demonstrator. And if we look at the half-lives they probe, they are longer than 10 to the 18 times 10 to the 25 years in the case of Gerda, and a little bit, about half of that in Majorana demonstrator. And so we are almost 2 orders of magnitude beyond this. Gerda has completely ruled out this result. So now we know for sure. Like, you might have looked at this before and been like, I want to know more. This was a target for a long time, right? People were trying to test this result. This was where the previous generation of neutrinoless double beta decay experiments that basically just have released their final results recently that you see here, that's really one of the targets that we were aiming for to test. And the germanium experiments test it most directly because you don't have to worry about the nuclear matrix elements, right? It's just a direct test of the half-life that they were claiming. So that Heidelberg-Moscow result is now completely ruled out. That's not a target anymore. And now we can say confidently that we have not, unfortunately, observed neutrinoless double beta decay. And yeah, so we also have results in tellurium from Quarry, that array of bolometers. We have results in xenon from both XO200, the TPC, and Camlan-Zen, the liquid scintillator experiment. And Camlan-Zen is actually the leading result right now. So to go beyond this level, so these are all at the 10 to the 25, 10 to the 26 year level, and we still haven't seen it. So of course we want to keep looking. We haven't even probed the inverted hierarchy yet. So we want to scale up. That's going to be the best way to improve our limits. And so the next goal is that 10 millielectron volt bottom of the inverted hierarchy, and that means we're going to the ton scale. So a ton of enriched isotope, typically watch for something like 10 years. And at the ton scale, our background restrictions become even more important, right? So not only do we want to scale up in mass, we also want to beat our backgrounds down. The problem is our backgrounds are sort of MeV, 1 to 2 to 3 MeV gamma rays. That's our primary background for most of these experiments. And they're just really hard to shield. We just live at sort of the minimum of the gamma interaction cross-section right there. So they're the hardest gamma rays to shield from. And you know, if you're familiar with dark matter experiments, they're playing a very different game, right? They're down here where those gamma rays those photons don't travel as far. So self-shielding works really well for them. It doesn't work nearly as well for us. And so, for example, the gamma ray interaction length in germanium is 4.6 centimeters. That's about, if you've seen a germanium diode detector, it's very comparable to the size of a germanium diode detector. So as our detectors get bigger, we can actually win in terms of having multiple interaction lengths. That's going to give us the ability to both take advantage of self-shielding and discriminate based on multiple scattering in our detector. So this doesn't work as well for these small, typically solid-state detectors that are highly segmented. It works really well, though, in a monolithic detector. So something like CAMLAND or a xenon TPC where you can scale up. Now we see that in xenon, I'll do this for xenon because that's really easy to scale up. So for a 5 kilogram detector, that's about where we're at the same interaction length as a gamma ray at our Q value, so 8.5 centimeters. And so here, we get no self-shielding at all, and probably this only interacts once in our detector. So we also have no ability to discriminate. At 150 kilograms, it's a scale of x of 200. Now we have a few interaction lengths. Our future detector next set will be 5 tons. And now we see we have lots of interaction lengths. So if most of our backgrounds are coming in from the edges of our detector, we are going to get to take advantage of some self-shielding effects, and we'll also definitely see multiple scatters. So that's one way that we can do background suppression, is by doing this topological discrimination between self-shielding and topological discrimination between signal and background. We also have, of course, the energy variable. So ultimately, that works for gamma backgrounds. It doesn't work for the true neutrino double beta decay background. So at the end of the day, if your energy resolution isn't good enough, your true neutrino double beta decay background will still kill you, and that's going to look exactly like your signal in the region of interest. So that does set a limit, or it sets a scale for what our energy resolution needs to be. So our goal for the ton scale will be something like 1 count per ton year. And so to achieve 1 count per ton year, we need a 1 sigma, we need a resolution of sort of 2% sigma over E to have less than 1 count in our region of interest. And we can push that even further. We can get it down to 0.1 counts per ton year if we get to 1% energy resolution. So it's not necessarily essential to get down to like 0.1% energy resolution, which we hear sometimes from the solid state detectors. They're also using that to discriminate background, but these large detectors have a different handle. And so it's really the interplay of all of these characteristics. It's not all about energy resolution. It is all about background. It's not all about energy resolution if you have another handle, like topology, if you have some kind of background discrimination aside from just the energy resolution. So I'm going to start a little tour of the experiments, which I'm sure you're all very excited about. I'm going to go through a long list of experiments, but I'll continue this tomorrow as well. But let's just take a look at those germanium diode experiments that ruled out the Heidelberg-Moscow experiment. So this is Gerda. I'm sorry, this is Gerda. So this is at Gran Sasso, and we see our detector in the middle of a water tank. It's not uncommon for these detectors to be in a water tank. That's just for shielding purposes. Gran Sasso is one of the medium deep laboratories. It's off a highway tunnel in Italy under a mountain. And we see a cryostat here. Cryostat is filled with liquid argon. Liquid argon provides a veto around the germanium diode detectors, but the germanium here, it's enriched in germanium-76, and it has various other kinds of shielding around it. But the sort of bare operation in liquid argon is their main technique that allows them to veto any other background that's coming in. So we have a very clean source around them. Oh, this is a better picture. So we've got that ultra pure water shield, and then inside that there is the liquid argon cryostat, so the liquid argon acting as a veto. And then inside that we have this, that argon is read out with these wavelength shifting fibers. There's also a shroud here. They actually were getting backgrounds implanted from radioactive contaminants in the liquid argon being attracted to their germanium detectors. So they ended up putting a shroud around each one of these as well. But in the middle, they have their germanium detector array. It's held with these very low mass holders because this, again, is a source of background that they want to eliminate. So they want to have as few non-active materials as possible around their detector. And this is their final result. So they wrapped up and they published their final result in 2020. They had 127 kilogram years of exposure. You can see that they are doing some background suppression. So if they just took their spectrum, they would have quite a bit of background. And this is their region of interest here. So they're able to do some active background rejection. They're able to do some discrimination between signal and background and knock their spectrum down to this level. So very low background, 5.2 times 10 to the minus 4 counts per keV kilogram year. If we zoom in on that region of interest, we can see again what an impact that had. And so there's sort of one count in their region of interest, which lets them set a limit, that limit we talked about earlier, 1.8 times 10 to the 26 years, a 90% confidence level. Very effectively ruling out Heidelberg-Moscow. Both Legend and Majorana Demonstrator have teamed up. They are now the Legend collaboration. Legend has actually started operating a Legend 200 experiment. So it looks a lot like Gerda, but it's going to have more mass. And they've also taken advantage of some of the low background electronics provided by the Majorana Demonstrator collaboration. Ultimately, what they want to do is build a ton scale detector, but I can see that I'm getting close to my time, and so I think I'll pick up with ton scale tomorrow. Yeah, you want to make a cut on that? You can. It's going to be similar to the energy cut. So yeah, they do play games like that. Absolutely. It's not 100% there. Like there's some spread on. You wouldn't want to do it completely. And actually, depending on the mechanism, you can get different angular distributions. So yeah, I should probably have shown one of the angular distributions for Neutrinoless double beta decay. But when they're doing their fit, the reason that they specify in their results here is that it's consistent with light Majorana neutrino exchange mechanism. It's because they're actually fitting all of those parameters. And they're fitting the predicted angular distribution for the light Majorana neutrino exchange mechanism at the same time that they're fitting the energy spectrum. So they are using that information. They're using the individual electron spectra, the total energy spectrum, and the this is sort of just a summary plot, but because they're measuring all of it, they're also using all of it. And so they actually, it matters for them what model they're using when they extract their limit. But their limit's consistent with this, but they didn't see anything, so it doesn't really mean anything.
By the way, I yesterday talked about this to you. So even if we get this Majorana effective mass to be less than the scale of the inverted ordering in that graph, normal ordering and inverted ordering. So even though we can't say that this has to be normal or inverted, the rate of this effective mass of the Neutrinoless double beta decay, if goes below to this inverted ordering scale,
yeah.
So can we say that it has to be inverted or normal ordering or not?
Right, so interpreting a null result is a pain. Because again, we always have to interpret it with the view that this only works for Majorana neutrinos. So this is why we're not sensitive to the hierarchy by ourselves. So if we do get down here and we haven't seen anything, either the effective mass is down here or neutrinos don't have Majorana masses. Right? Then we don't rule anything out. Or we got the nuclear physics wrong. So that's just the caveat for interpreting a null result is hard. Once we see it, that's easy to interpret. Neutrinos are Majorana. We've seen lepton number violation. We can put a line on this plot. But when we haven't seen it, it's a little tricky to interpret.
Okay.
If we knew for certain that we were, what?
Is there in the
Exactly. So if we knew for sure we were in the inverted hierarchy, then we could interpret a null result, right? Then if we got down here and we hadn't seen anything, but we knew they were up here, So we could say, okay, it looks like for some reason Majorana masses aren't there. We don't know why. But if they end up being in the normal hierarchy, just what you're pointing out, then we have this problem all the way down. Although I will say, I showed you that cartoon because it's kind of fun, but this very much depends on what +1 you've added. And so this is summing over a lot of things. So as we rule out what that +1 can look like, this doesn't always look this bad, right? So we're chewing up the sterile neutrino phase space. So it's not always necessarily that bad.
Okay, let us now thank Michelle again.